In conduction band, the electrons can move freely. So lowest unfilled energy level means that energy level where there are no electrons. Now, in this case, third one is forbidden band. Now we are calling it as a band, but if we check carefully, it is simply the band gap between valence band and conduction band. So how we can explain it? The two bands, that is conduction band and valence band, are separated by a region or gap is known as forbidden band. This band is collectively formed by a series of energy levels above top of the valence band and below the bottom of the conduction band. Remember that no electron can exist in the forbidden band. Now this is about the basic definitions of valence band, conduction band and forbidden band. Now we go to the next point, that is based on this band structure or band theory. By using the concept of this band theory, we are classifying the solids, which is the next one, that is classification of solids. If we see carefully, there are three terms, or we are classifying the solids into three terms. First is insulators, second is semiconductors, and third is conductors. Now they are based on the energy band gap between valence band and conduction band. First point is insulators. So in case of insulators, the forbidden energy band is wide, that is it varies from 5 to 10 electron volt. Due to this, electrons cannot jump easily from valence band to conduction band. In insulators, the valence electrons are bound very tightly to their parent atoms. Even in the presence of electric field, means if we apply the electric field to that particular material or specimen, electrons do not move from valence band to conduction band. Increase in temperature means certain materials are giving some response to the temperature increase. Means if we increase the temperature, then some electrons go from valence band to conduction band in some materials. That's why they are called as poor conductors, or we can say the insulators becomes poor conductors at high temperature, which is the first point we are discussing, that is insulators, which is shown in the figure with wide band gap. Then we move to the next term, that is semiconductors. Now what is meant by semiconductors? Semiconductors are nothing but the material which are in between insulators and conductors. In case of semiconductors, the forbidden band is very small. The forbidden band varies from 0.2 to 2.5 electron volt. A semiconductor material is the one whose electrical properties lie between insulators and conductors. When a small amount of energy is supplied, the electrons can easily jump from valence band to conduction band. We know that semiconductors are nothing but insulators at absolute zero temperature. When we consider the condition of room temperature or above that, then we are getting free electrons and that material becomes semiconductor. In semiconductor, charge carriers are both electrons and holes. For example, silicon and germanium for semiconductor. Then we go to the next point, that is conductors. In case of conductors, if we observe carefully figure, so there is no energy band gap or forbidden band. Actually, valence band and conduction band overlap each other. For electric conduction, plenty of electrons are available in case of conductors, as there is overlapping between valence band and conduction band, which are nothing but set of or series of energy levels. So electron can easily move from valence band to conduction band, and as conductor is, when we are considering, so due to absence of forbidden band, there is no structure to establish holes, means the total current in conductor is simply by flow of electrons, for example sodium, lithium, etc. So if we see carefully, so by using the band theory of semiconductors and the definition of valence band, conduction band and forbidden band, we have classified these solids into insulators, semiconductors and conductors. Now we move to the next important term, that is Fermi level. We have to check what is meant by Fermi level, its definition, and then we will discuss the derivation about Fermi level in intrinsic semiconductor. Now we start with the definition first. What is meant by exactly Fermi level? Fermi level is the energy that corresponds to the center of the conduction electrons and valence holes weighted according to their energies, or the Fermi level is also defined as a characteristic energy of the material. Means this Fermi level is a reference level which gives us idea about the semiconductor material and its charge carrier concentration in terms of holes and electrons. Fermi level is a characteristic energy of the material, we are saying. In case of an intrinsic semiconductor, there are an equal number of electrons and holes. Therefore, this Fermi level lies exactly at the middle of forbidden band, as shown in figure 1 for intrinsic semiconductor. When a donor impurity is added, donor impurity means fifth group element. We know that adding impurity is called as doping process, and it is called as donor because we are getting one extra electron when we add the donor impurity to intrinsic semiconductor. When a donor impurity is added to an intrinsic semiconductor, it becomes n-type semiconductor. Due to that, Fermi level shift towards the conduction band. Means if you see the figure number 2, that is n-type semiconductor, in that case just below the conduction band there is Fermi level and donor level. So donor level is formed because of adding impurity of donor atoms, and this Fermi level gets shifted towards the conduction band. Now why it happens? So as the number of electrons are more as compared to number of holes, that's why Fermi level shift towards the conduction band. Similarly, if you check the next case, next extrinsic semiconductor, that is p-type semiconductor, when an acceptor impurity is added to an intrinsic semiconductor, it becomes p-type. So acceptor impurity is nothing but third group element, or it is also called as trivalent impurity. What happens to an intrinsic semiconductor? It becomes p-type. Now it has more holes than electrons. This shifts the Fermi level towards the valence band. Now this is the case for p-type semiconductor where Fermi level shift towards valence band, it is just above the valence band, and acceptor level is formed due to addition of trivalent impurity. Now next point is Fermi-Dirac distribution function. So for Fermi-Dirac distribution function, when we are saying, it is also called as Fermi-Dirac probability distribution function. So this expression gives the distribution of electrons among the energy levels as a function of temperature, means it is temperature dependent, which is known as Fermi-Dirac distribution function. It is given by one simple equation, that is f of E is equal to 1 divided by 1 plus e raised to e minus ef divided by kt, where the function f of E indicates the probability that a particular quantum state at the energy level capital E is occupied by an electron. What is the exact meaning of this? Simply, if we consider the concept of probability, that is tossing a coin, we have 50% probability of getting heads and tails. Similarly, if we check the probability of that energy level, which may be or may not be occupied by electrons. So simply, theoretically, if we speak, if f of E is equal to 1, then that energy level is occupied by electrons, and if f of E is equal to 0, then it is an empty energy level. Now this is about Fermi level. Now we come to the next one, that is Fermi level in intrinsic semiconductor. There is a derivation for Fermi level in intrinsic semiconductor. Now we know that what is the position of Fermi level in intrinsic semiconductor, which is nothing but at the middle of valence band and conduction band. If we check the figure, then it indicates that the Fermi level is in the middle of valence band and conduction band. Assume that the width of the valence band and conduction band are small as compared to forbidden gap, that is energy band gap Eg. Now, since bandwidths are small, all levels in the band have the same energy. Means, instead of the band, we are considering that as a single energy level. In case of conduction band, it is Ec. In case of valence band, it is Ev. Energy, if we consider for all levels in valence band, it is 0, and for conduction band, it is Eg, as shown in figure. Now let at any temperature, capital T in Kelvin, capital N is equal to Nc plus Nv, where capital N is nothing but total number of electrons in both the bands. Nc is number of electrons in conduction band, and Nv is number of electrons in valence band. The number of electrons in conduction band is given as Nc is equal to capital N into P of Ec, where P of Ec is equal to probability that electron occupies energy Ec in conduction band. Means, if we consider that Fermi-Dirac probability distribution function, then we have P of Ec is equal to 1 divided by 1 plus e raised to Ec minus Ef divided by kt. So if we see carefully this Fermi-Dirac probability distribution function, so here f of E is equal to 1 divided by 1 plus e raised to capital E minus Ef divided by kt, and here we have written, instead of capital E, here in equation 2, denominator of RHS is e raised to Ec minus Ef divided by kt. Means, we are considering energy level, which is related to conduction band Ec, where k is Boltzmann constant. From equation 1 and 2, we are writing that Nc is equal to capital N divided by 1 plus e raised to Ec minus Ef divided by kt. Similarly, we can write for valence band, that is Nv is equal to capital N divided by 1 plus e raised to Ev minus Ef divided by kt, which is nothing but equation number 4. Now we move towards the next slide. If we consider the equation, that is we have written but n is equal to nc plus nv, we are saying, which is nothing but our first equation. So by using the value of nc and nv from equation 3 and 4 respectively, what we will get? Capital N is equal to capital N divided by 1 plus e raised to ec minus ef divided by kt plus capital N divided by 1 plus e raised to ev minus ef divided by kt. Simple mathematical adjustment or calculation is there. We have combined the denominators of RHS, shifted the product of that denominators on LHS, and we are getting the next equation, that is product of two brackets plus adjustment quantities on the RHS. Of course, the n is common on both the sides, so we have cancelled that n term. Now after solving the product of two brackets, we are getting LHS as shown in the slide below to the product of these two brackets, and RHS is as it is. Next equation or next step is nothing but the cancelling common terms on LHS and RHS. Whatever the remaining terms are there, we are showing in the next step. Now we have written one equation, that is e raised to ec plus ev minus twice ef divided by kt after combining the exponentials, and its value is 1, but 1 is nothing but also e raised to 0. For sake of simplicity, we have added this term. So if we put that value, that is 1 is equal to e raised to 0, and compare the two equations, simply we are getting ec plus ev minus twice ef divided by kt, which is equal to 0. Next step is ec plus ev, which is equal to twice ef, and after simplification we are getting ef is equal to ec plus ev divided by 2, which is equation number 5. Using the concept that we have discussed, as ec is equal to eg and ev is equal to 0, we get the next equation, that is ef is equal to eg by 2, and these two equations, that is equation number 5 and 6, gives us idea about the Fermi level, which is exactly lies in the middle of valence band and conduction band, which is nothing but ec plus ev by 2, or simply ef is equal to eg by 2. So we are mathematically proving that how this Fermi level lies exactly in the middle of valence band and conduction band. Now you have observed that how we have proved this equation, that is Fermi level lies in the middle of valence band and conduction band, ef is equal to eg by 2. Now one point is remaining related to this Fermi level, which is also important one, that is effect of variation of impurity concentration on Fermi level. We have observed in the initial slides that when we add the donor impurity and acceptor impurity, how the Fermi level shift towards conduction band and valence band. Now we check how the Fermi level shift towards the conduction band and valence band when we increase the impurity concentration. The addition of donor impurity to an intrinsic semiconductor leads to the formation of discrete donor levels below the bottom edge of the conduction band. We are discussing about n-type semiconductor first. In the first figure of this slide, you can easily check that at low level doping, at medium level doping, and at high level doping, how we are getting the response from Fermi level. At low impurity concentrations, the impurity atoms are separated from each other and they do not interact with each other as number of atoms are less. With an increase in impurity concentration, means if we start increasing the impurity concentration, what happens? With an increase in the impurity concentration, the impurity atoms separation in the crystal decreases and they start interacting with each other. Due to that, what happens? This donor level initially is a single energy levels. It goes under splitting, means it splits to form an energy band below the conduction band as shown in figure 1. What is the exact meaning of this? Initially, the number of atoms are less, so they are not interacting, but anyhow, they have formed their own energy level, that is donor level. But now, as we increase the impurity concentration, if you see the figure 1, medium level doping, that is middle part of n-type semiconductor figure, then you can check easily that instead of a single energy level, now it is a energy band. So the same thing we are saying here, and they are forming their own energy band. The larger the doping concentration, the broader is the impurity band. Means if we start or if we continue increasing the doping concentration, the impurity band or the impurity band gap increases. At one stage it overlaps on the conduction band as shown in figure. It means it go closer and closer to conduction band and overlaps the conduction band. In the figure we have observed this results in accessibility of upper vacant levels in conduction band. The donor electrons we are having or large number of electrons we are getting. Speaking about the Fermi level and the energy band gap width, the next point is the broadening of donor levels into a band is accompanied by a decrease in the width of forbidden gap. Means here as impurity concentration increases, energy band gap decreases. And also by the upward displacement of the Fermi level, means in case of n-type semiconductor, as impurity concentration increases, Fermi level moves closer and closer to the conduction band. And if we see carefully the position of Fermi level, it finally moves into the conduction band as the donor band overlaps the conduction band. In a similar way, means for p-type semiconductor, if we check figure number 2, at low level doping, at medium level doping, and at high level doping, if you see carefully the figure, initially the Fermi level is just above the valence band, then it go close to valence band, then it overlaps the valence band. Instead of acceptor level, now there is a acceptor band, and the effect of increase in the width of acceptor band, the energy band gap decreases in case of p-type semiconductor. So in a similar way, in p-type semiconductor, the acceptor level broaden and forms into a band with increasing impurity concentration, which ultimately overlaps on the valence band. The Fermi level moves down closer and closer to the valence band, and finally at very high impurity concentration it will shift into the valence band as shown in following figure. So if you observe carefully, you can easily get the details of n-type and p-type semiconductor. At low level impurity concentration, initially it is only a single energy level, Then in case of moderately doping concentration or medium level doping concentration, what we are getting? So we are getting the energy band of impurity atoms instead of energy level. Further, at high level doping, we can easily check there is a broadening of the band, that is donor band. Consequently, the Fermi level shift towards the conduction band for n-type and energy band gap decreases. In case of p-type semiconductor, if we see the figure at low level doping, medium level doping and high level doping, what we are getting? Here also Fermi level is close to valence band initially, and then it moves closer and closer to the valence band as doping concentration increases. Next, instead of single energy level, now there is a energy band for acceptor level. It becomes acceptor band, and furthermore at high level doping or as concentration increases, the width of acceptor band increases. Opposite to this, if we see the energy band gap, so as impurity concentration increases, energy band gap decreases. So conclusion of this slide is simply nothing but in case of n-type semiconductor, as impurity concentration increases, Fermi level shift closer and closer towards conduction band. For p-type, Fermi level shifts closer and closer to valence band. Okay, so this we are checking. Now we move towards the last point of this slide. This is the last but not the least, because it's a very important derivation which gives us idea about the concept related to semiconductor material, charge carrier concentration, what is meant by Hall voltage, and what is meant by Hall coefficient. So let us check this derivation one by one. So first we start with the definition of this concept or derivation, which is called as Hall effect. If a piece of metal or semiconductor carrying a current capital I, which is placed in a transverse magnetic field capital B, what happens? A potential difference is produced in a direction normal to both, that is perpendicular to both the current and the magnetic field. This phenomenon is known as the Hall effect, and the generated voltage is called as Hall voltage. So if you see the figure carefully, in that case or in that figure, we have considered one specimen of semiconductor. So let us complete first in the few lines. Let us consider a rectangular plate of a p-type semiconductor. So we have considered a rectangular plate of a p-type semiconductor. When a potential difference is applied across its ends, a current of strength capital I flows through it along the x-axis as shown in figure. So the definition is when we apply electric field and magnetic field both at a time, which is perpendicular to each other, then what happens? Perpendicular to both or normal to both electric and magnetic field, potential difference developed across the third axis, which is nothing but called as Hall effect. Generated voltage is called as Hall voltage. Now we have considered here p-type semiconductor material. So majority charge carriers are holes. In this p-type, you can see the holes deflection towards the front face. In figure, if you check voltage we have supplied, we are getting the current along the x-axis direction. Perpendicular to that, where we have applied the magnetic field, and we get the Hall voltage, which is normal to both electric and magnetic field. W is width and T is thickness for that specimen, which indicates the area of cross section for that particular specimen. Now let us define the current which is flowing through this p-type semiconductor or that specimen which is having certain specifications. If holes are the charge carriers in a p-type semiconductor, the current is given by capital I is equal to PAEVD, which is our equation 1, where P is equal to concentration of holes, capital A is area of cross section of the end face, that is capital A is nothing but width into thickness or W into T. E is charge on the hole. Vd is average drift velocity of holes. Next term is the current density, which is defined as Jx is equal to capital I upon capital A. So if you compare equation 1, then we can get the value of Jx as I divided by A is nothing but PEVD, which is equation number 2. So now we have two equations with us, equation for current and equation for current density, that is capital I is equal to PAEVD and Jx is equal to I upon A, which is equal to PEVD. So we are using this equation number 2 in our next steps for adjustment the terms. These we are discussing about electric field only or electric current only. Now the next slide we start with the theme, that is any plane perpendicular to the current flow direction is an equipotential surface. So here current flow direction means we have applied only electric field here. Therefore the potential difference between the front face capital F and rear face capital F dash is 0. Now we introduce the magnetic field, that is if a magnetic field capital B is applied normal to the crystal surface and also to the current flow, what happens? A transverse potential difference is produced between front face and rear face, that is capital F and F dash, which is called Hall voltage VH. So before the application of magnetic field, holes moves parallel to faces F and F dash, but when magnetic field capital B is applied, then holes experiences a deflection towards the front face. This happens due to the force generated by magnetic field, which is called as Lorentz force, denoted by Fl, and that force is given by, that is the magnitude of the magnetic force is given by F is equal to BEVD, where B is magnetic field induction, E is charge on the holes, Vd is average drift velocity. Now if we apply that magnetic field, that is Lorentz force, what happens? Because of this force, holes are deflected towards the front face and gets collected there or piles up there. Initially the material is electrically neutral. However, as holes gets collected towards the front face, a net negative charge or equivalent negative charge is remains on the rear face F dash. As a result, an electric field is produced across the two faces F and F dash. A condition of equilibrium will be reached when the force Fe due to transverse electric field EH balances the Lorentz force Fl. Means when we consider the force Fe which gets generated due to Hall field EH and it balances the Lorentz force, that is magnetic force, and the equilibrium condition gets reached, that transverse electric field EH is known as Hall field. So in equilibrium condition, when that magnetic force or Lorentz force balances the force due to Hall field, we are writing equation number 3, that is Fe is equal to Fl, equation number 3. Now we are writing the value of Fe as Fe is equal to small e into capital EH, or simply it is small e into Vh by W, where Fa is force due to Hall field, that is Eh, and Vh is nothing but Hall voltage, W is width of semiconductor plate. The force due to magnetic field of intensity capital B, we know that is Fl is equal to BeVd. From equation 2, we can just modify that equation as Vd is equal to Jx upon Pe. If we see the equation number 2 in previous slide, so it is Jx is equal to I upon A, which is equal to PeVd. So we are writing Vd is equal to Jx upon Pe by using equation number 2. So it becomes Fl is equal to Bjx upon P after adjustment, that is equation number 5. We go to the next slide. So equating equation 4 and 5 means, if we consider the equation 4 and 5 in equation 3, what we will get? We are getting E into Vh upon W, which is equal to Bjx upon P. We are interested in the Hall voltage value, so we are keeping Vh on LHS and shifting the remaining terms on RHS. We get equation 6 as Vh is equal to WBjX upon Pe. Now next equation we have written as WBI upon PEA, where instead of Jx means current density, we have written the value of Jx as I upon A, which is nothing but equation number 2. We have taken the reference. We have discussed already this. If T is the thickness of the semiconductor plate, then A is equal to WT. So we know that area of cross section of the end face is capital A, which is denoted by width into thickness, which is denoted by A is equal to W into T. So we are putting the value of A in equation 6 as W into T. What we are getting, that is the next equation. Vh is equal to WBgx upon Pe, or WBI upon Pe Wt. Deleting the common terms, numerator and denominator, that is W, we get Vh is equal to Bi upon Pet, that is new value of Vh. Equation 6 is also value of Vh, and equation 7, after simplification, we are getting new value. Now we are defining one new term, that is Hall coefficient. How we are defining that? Hall field per unit current density per unit magnetic induction is called as Hall coefficient. So this Hall coefficient is nothing but numerator Hall field is there, and in denominator there is product of current density and magnetic field induction. If you check carefully value of RH, that Hall coefficient is denoted by RH, so it is given by EH divided by Gx into B, but we know that EH is nothing but VH upon W, so VH upon W is equal divided by Gx into B. Now using equation 6, we have written value of VH as WBgx upon Pe. So after simplification, we are getting WBgx upon Pe into WBgx in the denominator as it is. After deleting the common terms, we are getting simply the value of RH as RH is equal to 1 upon Pe, which is equation number 8. Now using the value of RH, we are getting the new value of Vh, and what we get, that is using equation 7 and 8, what we get, Vh is equal to RH into Bi upon T, and RH is equal to Vht upon Bi. So we are getting the value of Vh in terms of RH, that is value of Hall voltage in terms of Hall coefficient, and of course Hall coefficient in terms of Hall voltage. So this Hall voltage is real voltage, and we can measure this with voltmeter by using a Hall effect setup. So friends, we have checked the points related to this concept, band theory and semiconductors, which is related to engineering physics. We have started with the formation of energy bands, what is meant by valence band and conduction band and energy band gap, then classification of solids, Fermi level, the details of Fermi level for intrinsic and extrinsic semiconductors. It's a derivation, that is derivation for intrinsic semiconductor, effect of impurity concentration on Fermi level, and the last one is the important derivation for Hall effect. So I hope that you are getting the ideas which I try to clear by using this presentation. Thank you very much and have a nice day.